In this video, we're going to continue our work in section 8.3 and look at example 7. This example is going to help set us up for our next convergence divergence test of series. So in this example, we're asked to discuss the convergence of the series, that is, the sum equals from n equals 1 to infinity of 1 over 2 to the n minus 1. So if we just look at these terms a little bit, we can ask ourselves, in this denominator, that's kind of where things are changing in our series. And we can ask kind of which is the dominant term there. And if we kind of reflect a little bit, we see that the 2n kind of takes over. Each term, we're always just subtracting 1. And after a long time, that term is just going to look a lot like 2 to the n. That 2 to the n will kind of dominate here. So this series looks similar to the series of n equals 1 to infinity of just 1 over 2 to the n. So I'm going to write that down. So this series looks similar to the series 1 over 2 to the n. And we can label n equals 1 to infinity. Okay, so what is that series? Have we met it before? Well, let's go ahead and take a look at a few of those terms in that series. So here we have 1 over 2 to the 1 plus 1 over 2 squared, which is 4, plus 1 over 2 cubed, which is 8, plus 1 over 2 to the 4th, which is 16, and we just continue like this. Okay, so do we recognize this series yet? We should. This is actually a geometric series, one of the first types of series that we met. So what is the common ratio here? So as we move from one term to the next, what number are we multiplying by? We multiply by 1/2. So here R, that common ratio, is 1/2. So then what do we know about the convergence or divergence of this geometric series? Well, it is a geometric series, and since that R is less than 1, but bigger than -1, we know this geometric series converges. So then we might conjecture that since this series converges, it probably behaves similar to this series. So our series must converge by comparison. I'm just going to write that down. So since the sum from 1 over 2 to the n converges, we conjecture, which is a fancy word for saying guess, we guess that our series, which is the summation of 1 over 2 to the n minus 1, also converges, probably also converges. Okay, so it turns out we can make comparisons between series to determine divergence or convergence. And we're going to make that formal in this next theorem. So this theorem is called the limit comparison test. So here, we're going to let A of n and B of n be two series with positive terms. Now, if the limit of the Bn over the An terms is equal to C, so some finite value, and we can say more for some constant C that is, so C has to have some certain or have special or particular properties. Those properties are that C is positive and finite. Then the series of A to the n's and the series of B to the n's either both converge or both diverge. So their behavior is the same. So a couple notes on this theorem. First of all, the purpose of this limit comparison is to choose a nice series of A to the n whose convergence or divergence is known. And then that will help you decide whether or not the given series B to the n converges. So we should think of this theorem, or how we should use this limit theorem, is to consider this Bn series as the series that's given to us. It's given to us and we're asked, so what about its convergence? So then we need to find an A to the n series where we know if it converges or diverges, such that this ratio is something that actually becomes positive and finite. Then we can determine what B to the n series does based on what A to the n does. Okay, we'll see some examples of this in some of the next videos. So the second note here, generally we choose a to the n to be a series that we have some information about. So some good choices are usually for us to choose a geometric series or a P series. These series are such that they're similar to the b to the n series so that that ratio does work out. And the reason why we either choose geometric or P series is because these are kind of in some ways the nicest series. They're the easiest for us to determine their convergence. And we're not going to get too much into this, but I do just want to give a little bit of an explanation for why this theorem should be true. So what this theorem does is it compares the a to the n and b to the n series. So it turns out that if there's a relationship between them, say a to the n series is less than or equal to the b to the n series, then if this series, say, converges, that would mean this one converges. So similar to that integral test that we set up, if that is the case, then when we kind of divide the b to the n, well, this side sort of becomes a constant, so the limits here become a constant. Okay, that's very brief, super hand wavy. There is a proof of this in our textbook, or you can probably just Google a way to show this. I can also provide a video if you're interested in seeing more details about why this theorem is true. For now, we can also just use it as a theorem in proving the convergence or divergence of series. So add this theorem to our toolbox as well.